So let me introduce the T core of the partition. So given a partition, lambda, a T core is a partition obtained by removing as many rim hooks of size T as possible. So for example, when T equals 3 and lambda equals 5, 4, 2, 2, the 3 core of lambda is 2, 1, 1, where I have shown a sequence of step of removing a 3 rim hook, a size 3 rim hook, to obtain a final partition where there is no cell of hook length, like corresponding to hook length 3, because 1, 2, this is 4 and 1. So a nice fact about core of a partition is that it is independent of the sequence of step you follow to obtain a partition which obtain the core which does not have any a hook of size 3 or size T in general. So
what is a reference for that claim?
So so there are many references. One would be projective combinatorics by Nicholas Lohr. In chapter, I don't remember, maybe 11 or something. But what I'm going to describe, like in some sense, you will see the proof of this as well along the way, like in the second part of my talk.
Okay.
I mean,
Thank you.
You can, once I talk about certain other things, it shows up. Okay, so now there might be slightly confusing notation. A partition is called a T core if the T core of the partition is itself. Basically, there are no rim hooks of size T. And a partition is, so this is probably a new notation, is called a T divisible partition if the T core of the partition is 0. So just to make sure everyone's on the same page, like if you have a T divisible partition, at least, like, you know, it's not necessary, but T must divides the size of lambda, because you're removing the size T rim hooks to obtain empty set. And we denote this calligraphic CTN and DTN to be the set of T cores and T divisible partitions of size n respectively. And we'll denote small CTN and small DTN to be the cardinality of the above set. So just to give an example, if you take T equals 3 and n equals 4, then T3, 4 is empty because, as I said earlier, T must divide. So 3 must divide the size of the partition, and there is no, like, 3 does not divide 4, so it's empty. While 3 core partitions are precisely 3, 1 and 2, 1, 1 out of the 5 partitions of 4. So I want to talk about something called partition division. So this is, again, this reference would be same as Nicholas Lohr, but you can, but what I'm going to describe, you may be able to see why this is true later on. So we denote P, dt, and Ct to be the union over all n of the corresponding set. So P is now set of partitions, dt is set of T divisible partition, and Ct is set of T core partition. Then there is a natural bijection delta T between the set of partitions and set of Cartesian product of set of T core partitions and set of T divisible partition, where the bijection is given. so I'll describe the second part later, but where the first part, the T core, uh, given a partition, the map gives the first coordinate should be the T core of the given partition, and uh, and the second coordinate would be T quotient. So this I have put in quotes because some like the usual definition of T quotient is a tuple of T partition, but I would like to think of it as a single T divisible partition. So we will go over the definition of this soon, but for what follows now, for the first part of the talk, we may not need it. And this satisfies some consistency with the weights in a sense that lambda, the size of lambda should be is same as sum of size of core plus sum of and sum of and the T quotient. So a general remark. So this can be thought of as a generalization of Euclidean division of natural numbers, where you can think of in this term, so you can think of it as a map from natural numbers to its remainder and its quotient. So that's where the motivation for the definition comes from. So a simple corollary to the above equality at the level of sets is the equality of generating function, is that generating function for the partition is same as product of generating function for the T cores and the one for uh, T divisible partition. So note that since I said that T divisible partition must satisfy T divides the size of partition, so this is empty for K. Not this T dt is 0 for K not equal to some multiple of T. So the following identities are known. So maybe so I'll not go into details, uh, uh, but it's so the the generating function for the T divisible partition is looks probably very similar to the generating function for partition, with just certain powers coming into picture. So it's basically and given that you can get certain the generating function for the T core partitions. Now, now what do we know? So our study, as if you have seen the abstract, is more of asymptotic study. So let's just recall that there's this famous
Could we
result
just
by
say the previous slide for just one more second, please?
yes.
Thank you.
So this is a celebrated result that number of partition is some exponent of square root of n with certain constants come into picture. And as you saw the generating function for dt, it's not surprising that a similar expression holds for the number of T divisible partitions as well. But when we come to number of T cores, the whole then it becomes very different in a sense that we do not have any such similar asymptotic results. It has to accompany with certain number theoretic sums, which I'm not going to discuss. Just to give a flavor that when t equals 2, then the number of T cores is 1 or 0, depending on whether n is a triangular number or, or it's not. Granville and Ono showed like there are a bunch of identities, but I'll just talk about C3n. It showed that it's certain sum of the T D3, which is where the symbol is the Jacobi symbol from number theory. And they also showed this was conjecture for a while back, I think in 90s, that to show that for t greater than 3, this is at least this is positive. And in that paper, they also showed that 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 the number of t cores for of size n for any n and t greater than 3, these are positive. So clearly, like, and the such kind of expression may be much harder to. I mean, but CT, the number of t cores behave much more erratically than number of partitions. Okay, so this is where our first theorem.
Sorry, just
yeah.
what is n in the conjecture? Any n?
Yeah, so n should be positive.
Any, okay.
Okay. So this is not a conjecture anymore. So this is proven like for a long time. But there are some other conjectures relating, like comparing the numbers for different, like different CTNs. But let's not go into that.
So, Shubham,
Yeah.
do you know any characterization of such partition? Like when we know what are the two cores, right? They are a staircase. So, do you know any other?
So this is so the triangular numbers come from the staircase partition.
Yeah.
The characterization, in a sense, that so in terms of, so it depends on what, like, so one way is just by definition it's the partitions which does not have a hook of hook length divisible by t.
Yeah.
There's another way to look at it is using abaci or abacus, which I'm going to discuss in my talk. And if you just care for the number, then you can write certain equation, some quadratic equation here, and the solution of that quadratic equation shall give you the number of t cores of that size. So there are three ways to deal with this. I mean, so using the definition, using abacus, which we'll discuss, and using using certain solution of for t minus 1 variable, some certain quadratic equation. So the solution gives you the number of
So actually, I was not asking about the number itself. I was asking, do you know the characterization of such partitions? Like, what are the partitions which have empty three cores? Like we have for two cores, we have the staircase partitions, right?
Yeah. So I think I don't know if to give better answer than the characterization in terms of abacus, I would say. So we'll see that later in the talk.
Okay, thank you.
Okay. So so now let's define this this sum, capital CTN, which is certain sum of the number of t cores. So to begin with, it may seem strange as to why we are taking certain sum, and also why are we hopping by t steps while taking sum. But this has a combinatorial reason. The reason is that just recall the partition division. So this is in bijection with the number of set of partitions, and you can look at the project. Basically, given a partition, you look at the t core of that partition. So this number is precisely counting the size of the projection of. So if you fix a partition, if you look at the image is the size of that, the projection of the image to the set of T cores. To be more precise, so it's basically set of all T core partitions, which comes as a T core of certain partition of size n. So a remark, when T is prime, then this defines the number of, so I'll not go into detail of this because it will be not relevant for the talk, but this defines the number of T blocks in the T modular representation theory of the symmetric group. So this is our first theorem, which will help us prove the next one, which is probably the main result. So we showed an asymptotic formula for this sum of this certain sum of Ct of n, and it's given by this expression. It says it grows as n power t minus 1 over 2, and there are some factors coming into picture. So for the proof of this, you can go over our paper mentioned in the link is given in the web page. So now let's now try to see how, like, what is the distribution of size of T cores for a uniformly random partition. So let's define a random variable which sees the size of T core. So basically, you take a uniformly random partition lambda, and yn be a random variable which gives you the size of the T core of that partition. Then, so this is a discrete random variable, and you can, if you like, you can see it as a probability mass function given by mu and k to be all lambda partition of n, such that the size of its core is k over Pn. So we are looking at over set of partitions of n. So you have to divide by Pn if you want to look at the probability mass function. And so if you recall the partition division, so this is what you get. It's the number of T cores of size k times number of T divisible partition of size n minus k over Pn. So we are interested in certain convergence of these random variables as n goes to infinity. But since, I mean, as what you usually do, for example, for binomial distribution and so on, if you want to talk about certain convergence, you have to scale it in a certain way so that you can make a precise statement. Okay, so this is, so we define a new continuous random variable xn with the probability density given by scaling the domain by square root n, like, which is here, and then scaling the function by square root n, so that you finally get the integral to be 1. So once you scale this and you get this new random variable, what we see is that this random variable xn converges weakly to the gamma distribution random variable with shape parameter alpha and rate parameter beta. So what is this gamma distribution? Is simply given by the density function to be some power of x times exponential, like negative exponential of x up to some constants, where this beta and alpha are the constant given here. Here gamma is the usual gamma function, and so note that here we are talking about weak convergence, and you can, for some silly reasons, you can see that like there is no hope for, at least straightforward, no hope for any better convergence than this. So here's the plot for cumulative density function, which is where you can see for various n, we see that it converges to the to the gamma distribution, which is mentioned in the red line. And here is the plot for the density function of both of the two. And since, as I mentioned, that many times these step functions become zero, so there's no hope as such for convergence, like strong convergence. But so okay, so basically we understand the distribution of the size of T cores, and this gives a nice corollary. Or here I just said a theorem. If like this was the main motivation to study that, and we found that it's gamma distribution. But what we find is that this expected size of T core for uniformly random partition, if you take like a big partition and you take the core, like you can run the program on Sage if you like, then you see that it's the size of the T core is asymptotic to this nice looking value, which is of the order of square root n. So what we are saying is that the core of a partition is in expectation grows as square root n, where the partition grows as n. So it's much smaller content than the actual partition in expectation. So here's the plot for three core for a partition. The expected size given with the dotted blue points, and the red points are just the function given here. As you can see, it nicely converges with a factor of 1 over t power 1 over 4. But maybe let's not go to the error term. So we will. So for the purpose of this talk, we will not go through the proof of these main theorems about the distribution. So the proof is much more technical and more analytic, in a sense that you have to make a lot of bounds and then get these results. So instead we'll use this to talk about, to do some more combinatorics of random of uniformly random partition. So before we start, let me briefly introduce.
Can I ask you a possibly very naive question?
Yeah, sure.
So there are some points that stand out below your curve.
Yes.
Is there some? What are those values of n? Is there something that you can? They seem to form a nice curve themselves. Just
yeah,
like
that's true. So this this might okay, so I don't remember exactly what these points are, but my guess would be that these point to be possibly the three the number is divisible by 3, or because then the core size, so when you take the random core, then it has the possibility of being empty. That means you have a bigger chunk of a partition being the T divisible partitions. But or maybe actually I'm talking about the upper one. The bottom one might be the ones which are 1 mod 0. But I have to be like, maybe I should not make any statement here. I don't know what these points are. but yeah, it can be investigated as well. Okay. So let's quickly, briefly describe another way of looking at partitions, which for me is actually more convenient. I mean, I find it quite enlightening, this perspective of looking at partitions. But what is abacus? Let's start with that, and then we'll see how partitions are in projection with certain abacus. So, so an abacus, or sometimes like called one-runner abacus, is a function from integers to 0, 1. So it's basically a sequence in extending in both directions uh, of 0 and 1, where you impose a condition that for integer much lesser than 0, like on the left hand side, it stabilizes as 1, and uh, and the function stabilizes 0 on the right hand side. And we say W is justified at position P if there exists a position where on the left of it it's all 1, and on the right and itself is all 0. So in this case, so let me just describe you in the example how we are telling you how we are giving this as a function. Here the underscore will always mean the position 0 for the function, and then you can I mean, that just gives you the description for the function when you write in this form. And since it stabilizes after some time, you just have to write finitely many of them. And we say that abacus is balanced if when you slide all the ones to your left, like think of sliding as swapping with 0, 1, like just next to each other. So when you slide all the way, you'll always get a justified abacus, but the justification is at 0. So it's basically the equal number. So if you take large enough region from plus m to minus m, minus m plus 1, you'll get equal number of ones and zeros. So that's where the word balance comes from. So let me briefly describe you how partitions and
Sorry, I did not
yes.
follow. I did not follow. So
Okay.
what is to a justified by moving ones to the
So this
okay, got it.
so there is a
I understood. Thank you.
yeah, okay.
Understood.
So you move all the way. Okay, so this is a well-known theorem, again can be found in projective combinatorics, that partitions and balanced apici are in bijection. So let me show this to you. So how you think of this bijection is that think of 0 as the left. I mean, actually it depends. Sometimes people prefer from the bottom. But think of walking along the partition. And as you see, after some time, you'll always be going down. So the left would correspond to a 0, and the down will correspond to a 1. If you like, you can do up and right. So you start off with many zeros, and when you hit it down, so this is your 1, then this is your 0, this is 1, 1, this is 0, 0, 0, 1, 0. Sorry, I think this I made. Oh no, that's correct. Yeah, and so on. So it will go all the way up to ones. So as you see, if you want to read it off as an apici, it would simply be an infinite numbers of zeros, and then you have 1, say 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1. So this describes you the partition. Like for a given partition, you get this abaci. And as you can see, this description is up to translation. So that's why if you translate it, it gives you the same, two partitions gives you the same description. So you want to make sure that there is some kind of balance. So that's where the balance comes from. In a sense that you have to fix one of them. And so so basically we are looking at partitions now in this abacus in one runners. And so let me briefly tell you why it is useful in the case when you talk about hooks and hook lengths, is that if you take a cell C, for example, which is denoted here C, that this C is can be thought in terms of abaci. What does it refer to? It refers to a pair of 0, 1, which is so what is this pair? So if you look at the corresponding hook, where the two, so on the when you go to the right, it will end up with a down arrow, which will be a description of a 1, and when you go down, it will end up with a left arrow, which will give you a description of 0. So in this case, this the rim hook or hook corresponding, or the cell corresponding to C is given by this pair 0, 1. And now notice that if you so removing a rim hook, so the hook length is given by the distance between those, because it's the it's the path from this from one corner to the other, which is described here. So the distance between the position of 0, 1 gives you the size, and removing this rim hook simply translates to swapping these two numbers. So here I showed you the removed picture, and then if you want to work it out, it's just swapping 1 and 0. So there is a nice and easy description of removing rim hook in terms of abacus. Now, since we are interested in swapping only, we are fixing T, and we are interested in swapping only the size T rim hooks, which will be hooks of size, so it will correspond to positions which are T apart. So you can break it up, the one-runner abacus into T tuples, where the positions are I mod T. So for example, when you take T to be 3 and lambda to be 5, 4, 2, 2, then so let's describe lambda 0, for example. So it would be the sequence which is given by the one which I'm marking here. So you just hop 3 of them, like by 3, and you look at the subsequence or sub abacus of that. And then lambda 1 would simply be the translated by 1. You do the same thing. You look at this subsequence, and that would give you your lambda 1. So since you're interested in the T core, so since we are interested in the T core, so what does, so recall the T core is removing rim hooks. So it would simply corresponds to, to moving these, sliding these ones, so by distance 3, right? So in the 3 runner, it would simply correspond to moving ones of each row of the T runner. And once you have moved all the way, so you'll see that those will be precisely justified partitions, justified abacus. And for those justified abacus, you can, so in general, like a T core partition is given by by a one runner whose corresponding t runner is simply t rows of certain justify abacus. But justify abacus information is given simply by the position of justification. So those we call it say P0, P1, and P2. So which is in this case it's going to be which is -1. So this is -1 position, 1 and 0. And you can see that its summation pi will be 0. So as I promised earlier that I'll define T quotient partition. It's nothing but you look at this the partition. You look at the corresponding T runner, and the corresponding T runner. If you look at each row of the T runner, and you make it balanced, basically you shift enough so that each row becomes balanced. So for example, this is -1, so you shift this by 1. This is already balanced. Sorry, this is not balanced by 1. So you shift this by -1, and then this you will keep it the same because this is balanced. To obtain this tuple of one runners, which will give you the T runner, and the corresponding partition to this is precisely denoted as, is defined to be T quotient partition. One note is that so given the T quotient and the T core, so T core tells you how much you shift, and T quotient describes you precisely the shape of each row, like of how the abacus of lambda looks like. So it's clearly a bijection between when you're given row the T core and a T divisible. So here this is T divisible partition. Like when you just balance each row is because when you justify, that means when you remove the T cores, what you end up with is the balanced one runner corresponding to it. So these V's are these news are T divisible partitions. Any question? So this was a background on abacus, but now let's go to the main result. So now this will be very useful. So now since we have developed the dictionary for what we need, we can start with stating at least the corollary to the so now recall that the cells sorry the T course of a partition in expectation is small in number. It's order of square root n. So this can be used to give a very nice corollary which says that for a random partition lambda, and you take a random cell, and you if you want to talk about the probability, so you want to obtain the probability of this random cell in random partition and the hook length of that cell to be divisible by t, then it's going to be 1 over t in when n is large enough. So it's basically saying that the hook length of a cell is independent of, in some sense, is what you would expect in general if it's randomly distributed for over modulo t. So why this follows is that so for a random partition, for a partition in general, the number of cells. So if you remove a T rim hook, is same as removing like will result in removing or decreasing the number of cells with rim hook divisible by T by exactly 1. So this can be for if you follow up the discussion on abacus, you can see that. And so you basically keep removing T hook unless you don't have a rim hook divisible by the size of it, which is divisible by T. So that's precisely the core. So basically the cells in lambda which are whose uh, hook length is uh, divisible by t is precisely n minus the size of the core over t. This the probability is, since the expectation of the size of the core grows as square root n, you'll see that as n goes to infinity, you get 1 over t. So this was nice, and this is a simple corollary to the main result of our paper. But what happens when we ask not just divisibility by t but any modulo class? Then the above proof breaks down because of this. So let me show you this example. When you take lambda to be 6, 4, 3, 1. Yeah. So does anyone
Sorry,
have a question? Yeah.
can we just go back one slide, please?
Yeah.
So I'm a little confused because when t is larger than n, this is not possible, right? T is, I
So
don't
when
know.
t is larger than n, then the t core would simply be itself.
Mhm.
So this will be 0. And that is true because there can't be a hook, there can't be a cell with hook length of size t.
Yeah, but what does the corollary itself say in that case?
Oh, so here we are fixing t. So for all purposes,
Okay.
we fix t. And when n goes large enough, so
That's
the
the range. Okay.
situation,
Okay.
yeah.
Thanks.
Okay. So now, so why the above proof doesn't work is because of this example. So I've given a partition, and then you have these hook lengths marked for each cells. And when you remove it, say 4 hook in this case, what you obtain the hook lengths obviously change, like in a strange manner. Like uh, it affects not just the cells which we remove, but the rest of the cells. And if you see how many, so removing these 4 cells, how many hook lengths are removed for each modulo classes. So for things divisible by 4, it exactly goes down by 1, as we mentioned earlier. But that's not the case for other modulo classes. In this case, it works for 2, but for these two modulo classes, like mod 3, uh, that's not the case. For example, for 1, it goes from 5 to 3, and for 3, it remains the same. So we had to develop some new tools to deal with this, and my main focus will be to tell you that these tools, I mean, whether you care about this problem or not, but the tools might be is something which we didn't find anywhere, and it might be useful to follow such studies. So just a reminder that what partition division is and what these DTs are. It's a set of T divisible partition. So there is an action of the permutation group ST on the set of T divisible partition of size n. So how does this action go? Is basically you're permuting the T runner, the rows of the T runners. So here there might be a slight problem with the notation, but I'm using the indices, permitting the indices from 0 to t minus 1 instead of 1 to t, which is the conventional notation. So you basically, this permitting this t runner gives you this another t runner, and you can show that the size is preserved under this action. So it certainly gives an action on the t divisible partitions. And we can extend this definition to give an action on the set of partitions Pn of size n, given by given using the partition division, so you basically keep the core fixed, and you use the action on the quotient. Yeah, so just
So,
here.
so this action of ST on TTN, so this is giving an action on the uh, quotients, right?
Yeah.
So the question is, if you change the ordering of the tuple in a quotient, do you
Yes.
know how the partition will change?
So, I mean, um, it like I'm not sure like how specific can I be, like, but like this is all, like I prefer to think in terms of the T runner, and the size of the partition will be same, but I can't visually tell you in Young diagram how the partition changes.
Okay.
Although, so this is for just T divisible partition. So here we are being careful. So we are not changing for a general partition. We are not changing. We are not permuting the uh, the T runner. We are keeping the core aside and permuting the T tuple quotient. I don't know. Maybe like it's something which can be worked out. Like it's so this is certainly I've not seen much work on this. I mean, I've not seen this kind of things done before,
Okay.
but it's like maybe it's like some, I don't know anyone who has worked on these things. So that's why I said like this. What tools we are going to discuss now is something which has potential of actually working out more in being worked out in more details. So we have this action of permutation group on set of partitions of size n. So in some sense, so for example, like just to say, uh, the T cores of size n are fixed point under this action, but there can be more fixed points. So I'm not saying those are all the fixed point, but those constitute certain fixed points. Like those will be fixed under this action. Uh, Now we define this thing called B smoothing of a T divisible partition. So we denote it with C subscript nu superscript P. So this is a union of cells in the Young diagram of nu, whose corresponding 0, 1 pair are at least B plus 1 columns apart in the T runner, abacus of nu. So here basically you're saying, so let's look at the zero smoothing. So we look at the example, the partition 732, which is a 3 divisible partition. And zero smoothing will be, you look at the cells which correspond uh, to the pair 0, 1, which are at least 1 apart. So for example, so I did not mention before, but if you want to get the first row in the Young partition, you just have to count the number of zeros which is on the left of the rightmost one. So in this case, it would simply be 7 because nothing happens. But what about the second row? So you have a 1 here, and you're looking at, so previously there were uh, three cells in that row, in the second row of the Young diagram, but from by the definition, like you don't count for the one which is in the same column. So you get 0, 0, 1. So there's the 7, 2. And if you want to do the same for 1 smoothing, that would be cells corresponding to things which are 2 apart. So in this case, this 1 will correspond to these 4 zeros. So that will give you 4, and the rest does not have anything 2 apart. To look to the left. So this is an example for this certain partition and of the B smoothing. So what is interesting about B smoothing is that if you take sigma to be in S3, And if you act on these rows, the B smoothing does not change. It's invariant under this action. Also, I didn't tell you, but one more thing, what you can see is that these B smoothings are subpartitions of mu. So there are two things. So there's a subpartition which are invariant under this action of the permutation group on the T-divisible partition. So the C nu B gives you a sequence of subpartition of T-divisible partition, and as I mentioned, it's invariant under the action, the natural action defined above. Now there is this lemma. So if you want to come back to what we are trying to show, the uniformly random cells C in a random. So if you fix a T-divisible partition, and if you look at a random cell, the probability that the hook length is congruent to I mod T is independent of I when I is not 0. So this just follows because, so let me give you an example to show why this is true. So if you take 1 and 0, and remember this, the pair 1, 0, and then when you act with certain sigma on this tuple, so the positions will change, like, and it will go to different correspond to different cells because of different partitions. But what is the hook length of this pair 0, 1, the corresponding cell in the M diagram, is actually just depends on the position of these of 0 and 1 in the T runner. Like it only depends on which row it is in, and when you permute it, it changes. You can change it to a different modulo class. Basically, it permutes all of it as long as they are not in the same row. And if you take a T orbit of ST orbit, then you will see that you will get all the partitions, like for the given marked cell, which will be in each of the so these are in the smoothing, right? So these are, as I said earlier, these are invariant. So these are sub partition of these partitions for all up to, like, when you act with sigma. So you get a bunch of partitions, and the subpartitions are invariant, and these cells will permute the modulo class just by permuting the position of the rows where 0 and 1 lie. Any questions? Okay, so in this case, for example, if you take 0 and 1 coming from here, what you see is that for the partition 732 is
maybe I'll ask you a question. Perhaps it
yes.
is too naive, but nevertheless,
Yeah.
Just to slow you down a little bit, if for nothing else.
Okay.
So this sequence of these C, whatever you call them, nu
Yeah.
B, B nu, those are
Yes.
invariant under the action, right? So
Yes.
can for two different orbits, these numbers can be the same. This sequence can be the same.
Yes, they can be the same.
They can be.
So,
Okay.
for example, if you just had different, so C0, let's just look at C0. It only, so how do you obtain the T runner for C0? You push all these, so you push all these ones to your up, and when you have the, so all the partitions which correspond to the same T, like the T runner where everything is pushed up, and looked at the corresponding partition, that will give you the C0. So it certainly can be the same. So it doesn't, the sequence does not give you the full description of the orbit. Okay, so where was I? So in this case, you have this hook length to be 8, which is 1 mod 3, and when you change the row, you get this cell which is whose hook length is 10, which is so sorry, this was 2 mod 3, and this is 1 mod 3. Now for so this was done for a T divisible partition, but now we want to look at this row and U and look at this. So we have this action here as well, but we want to say something is a it's okay. So we say something is a canonical smoothing, which is a canonical smoothing is a subpartition of the quotient partition, which is where B, you want some B smoothing, where B is the maximum of the difference between Pi and Pj, where Pi and Pj, if you recall, for any so this B lambda depends on the row, is the difference between the position of the rightmost 1 and the leftmost 0 plus 1. So for example, in this case, if you have these P0, P1, P2, so for partition 1, which is a 3 core, you get 1, 0, minus 1, and so B lambda will be 2. So we call, so this is, so note that, okay, so maybe I didn't mention earlier. So this is not true. So a T divisible partition, the T quotient partition, nu is not a subpartition of lambda. So this set cannot be viewed as a subpartition of the original partition lambda. It's only the subpartition of nu. So now we have described this canonical smoothing. So let's look at what canonical smoothing would look like for the partition 10,3, nu is 732, which we have been dealing with so far, and rho is 1. So that gives you, as we saw earlier, the B lambda to be 2. So things which are 2 apart. So it will be the canonical smoothing will consist of just 2 cells. And so these are precisely the 2 cells. Now, so why did we take this strange definition of looking things which are like these maximum of Pi minus Pj? Is because of this. So here you were at the T quotient, and you look at these zeros, ones, and you obtain lambda, as I mentioned earlier, by shifting. So for example, for shifting these T quotients by appropriate number, which depends on the core. So for example, this is shifted by 1, the second row is shifted by -1, and this third row remain the same. No, sorry, I think this is 0 and this is -1. My bad. So this is not shifted, and this is shifted -1. So you can remember the positions, and you can consider these cells in your original lambda as well. So for this particular example, you start off with x and y being cells which correspond to the 0, 1 pair, and that would give you some cells x and y in the original lambda 3, original lambda 10,3. And what we see is that, so basically what it achieves is we get an injective map of C lambda into, so C lambda, okay, so C lambda was a subset of nu. So we get some map which takes C lambda to lambda injectively. So just by remembering these positions. But remembering the positions actually if you recall that the corresponding hook length only depends on the position in the row of these 0, 1, which is not changed. So the hook length remains invariant under this phi, which takes some cells C to phi C. So in this case, X has hook length 9, which remains same in this case, and Y, which had hook length 8, goes to H goes to the hook length, which is 11 in this case. So you see that it's just increased by 3. So here we are taking t equals 3. So that gives us the same modulo class. So what is the benefit of doing this canonical smoothing in our case is that for uniformly random cells C, the C in the image of this canonical smoothing, which we saw earlier that the hook length does not depend on the modulo class, like the probability of hook length being I mod t. So this clearly translates because this phi does not change the congruent classes, sorry, modulo classes. So it is enough to show that if you want to show for a random cell C in a random partition lambda, if you want to show it is independent, the modulo class is independent of I, you have to show in some sense that phi C constitute most of lambda. So you have this lambda, you have these cells, which in some sense does not distribute the modulo classes equidistributed for I not equal to 0. If you say those are all the cells, then you're done. So I am running out of time now, I suppose. Let me briefly tell you why this is the case. So this is the case. So this is some lemma which I'm not proving. It basically says if you have some lambda, and if you take some smoothing. So okay, so I'm drawing very bad pictures, but so that will give you some corner cells, like and that is smaller number. So basically what we are saying is that, so this is nu, by the way. So nu minus c lambda will be of order t times b lambda plus 1 times root n. And a simple count, so b lambda depends only on the core. So you can see that, like, you can do a simple count to show that it's less than some square root of core. So C, the smoothing, is basically all of it, except for this square root of core times square root of n coming into picture. Like the difference, the boundary is of this size. And since we have seen earlier that expected size of the core is square root n, so b lambda will be of n power 1 over 4, and this order, which is given by this, is going to be order of n power 3 over 4. So we obtain what we wanted. It is the majority of the cells, and that as I noted, that independency of modular class with respect to I for I not 0, and the first result which we prove for I equals 0, that's the probability is 1 over t, we get our result for that a random cell in a random partition lambda, the probability of hook length to be I mod t is exactly 1 over t. So this is the end of my talk, and I'll just try to summarize what we have done and what to take away from this talk. So first thing is that this is something which I didn't cover in much detail, but we showed that we showed asymptotics of distribution of the size of t cores of uniformly random partition on sorry, this should be Pn on which can, so the distribution converges to a gamma distribution as n goes to large enough, and this is obviously up to scaling. The second point we noted was that the expected size of the size of a random T core, like for any random lambda, uniformly random lambda, the size of T core grows as square root n in expectation. Thirdly, so this is what I spend most part of the talk, is describing this new construction called the B-smoothing, and also the action of permutation group, which has potential to be explored much further. So this is something which we discussed, and at the end, like we showed this nice result that Hooke's lengths are randomly distributed over modulo plus t. As I mean, all of these are as n tends to infinity. So these may look as expected, but if you think about it, if you take a core partition, then this is certainly not true because there is no modulo plus 0 in the Hooke length. So it clearly uses the fact that the cores are very small in expectation. Okay, thank you, and please let me know if you have any questions.
I have a quick question about the
Yes.
expected value result that you had. Yes. So the core T of lambda is itself a partition. So when you say the expected value is this T minus
sorry,
1.
This should be size.
Okay, the size. Right, okay, and maybe I could ask one follow-up question to this. So this core construction, I mean, if you apply the core T operation to partitions of size lambda, you're getting partitions of various sizes. They're not all concentrated in one level.
Yes.
So to speak, right?
Yeah.
So can you use your asymptotic formula, your gamma distribution, to sort of say something about the number of T cores in a given level? Say, so for example, take a level, say partitions of size M sort of big, and then say take much larger partitions, size N, which is much larger than M, and then you do this core construction and look at the distribution at level M.
Yeah.
Do you know something about this?
So, so if I'm clear, you're asking if you take M to be very less than N.
Yes.
And you want me to, you're asking the course of, so lambda be a partition of N.
Yes.
And you're asking the size to be M, or?
I want the size of that to be M.
Yeah, so when the size of this core is M, then number of such things are given by this dt, which is the number of T divisible partition of N minus M.
Right, but you'll get
C. You also get the number of cores of size M.
Yes.
So this is something which is coming from partition division.
Right, but you, okay, so that's the number that live at level M, but my question, you'll get some interesting probability distribution at level M, right? Each.
Okay, so yeah, so this is something which can be further studied, that instead of just looking at size N, size of core, like over the course of size M, this is something which we haven't yet studied, but it would be interesting to study.
Is it possible that it's, I mean, there are these various distributions that show up where you.
Oh, no. Oh, sorry. Okay, so my bad. It will be same for each core. Okay, so that also follows from partition division. if you take two, so row 1 and row 2, be two T core of size m, then the number of lambda in n, which gives you row 1, is same as number of lambda, which gives you row 2. So
Oh,
it's
so
equidistributed. Yeah.
Okay.
Uh, yeah. So that comes from this abacus construction, that it just sees if you like this partition division, when you fix row, then what you have to do is this fix, like, find all these possible news. So, and these news does not can vary anywhere in this DT. So this formula kind of encaptures that in some sense.
Okay, so you're saying that if row and one, row two, both, of course, they have the same number of preeminences.
Yeah.
But it's possible that row one is not a T core. So I mean, you still have a kind of you still have you have things of zero probability, so to speak, and things of.
Oh, okay, yeah, that's true. Like, yeah. So you'll have 0 and the number dt and n minus 1 m coming up.
Thank you.
Yeah, thanks. I have a question. Have you looked at joint distributions with respect to different T and T1 and T2? Have you experimented with that?
So we have, so like when you say like you want to look at the T core, like T1 and cores and T2 cores, and then look at the size together.
Yeah.
No, we haven't looked at that so far. So yeah, we haven't studied that yet.
I don't know, like would they be appear to be somewhat independent, or yeah, that's sort of the question.
So that's interesting, because as far as how like one would hope that they are independent, but actually not. So because if you take, say, T1 equals 2 and T2 equals some multiple of 2, say 4.
Well, yeah.
Then,
okay.
like if you take co-prime numbers, then there is
Co-prime, yeah.
Yeah. Yeah, one would expect it to be like we haven't seen it, but yeah, this will be nice to show, maybe to show if for T1 and T2 co-prime to be the the distribution, the joint distribution to be independent. But that's something which we have to look at. So thanks for the question.
So I have a kind of unrelated question. For T equals 2, is there like a simpler rule to express the sub-partition filtration thing that you were talking about?
So for T equals 2, so if we just look at the zero smoothing, so let me go back to that slide. So as I said, like if you have just two of them, if you look at zero smoothing, it's just pushing the ones up. But I don't know if what that would correspond to in Young diagram. So you're basically pushing everything up as much as you can. Like that's true for all zero smoothing.
So you would get you would get a new 2 hook on one of the partitions, and then you would lose a 2 hook on the other one.
Yeah. So yeah, you lose certain two, like.
Sorry, everything would shrink by 2. Whatever the hooks would shrink by 2 in one of them, and then they would only shrink by 1.
I think it's not. It might not be that like. I think it might be a bit more complicated than that.
It depends on the column, right?
Yeah. So I mean, maybe I can. I mean, if you take, for example, I don't know. So let's just take 2 1. So that is so 1 1 0 1 0 1. So it's corresponding, although this is, okay, so my bad, I should take something which is divisible by, which is t divisible. So let's look at 3, 1. I mean, this is something maybe we should, like, one can do it. Like, I think it just needs to be worked out. Like, I don't know any good answer to that. Maybe I can work it out, but maybe it's not a good idea to do that now.
Okay, thanks.
Yeah.
Okay, any further questions?
So I don't know, is this like the first sort of probabilistic analysis of
So as far as I know, like, I haven't seen any other paper dealing with the probability of these kind of distributions.
it's very, very, very beautiful. Thank you.
Yeah, thank you.
Okay, so maybe we'll thank Shubham again for this nice talk.
Okay, so that's very nice.
Yeah, very nice results. Yeah, I like them too.
Thank you.
Okay, thank you all.
Thank you.
Bye.
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 Yeah.